Welcome back. Hope you guys were able to enjoy your snow day. Or maybe a bunch of online classes. I don't know. Have you guys looked at the homework so far?
Tonight.
It's sort of an awkward homework. I had trouble assigning it because we really didn't do any math last week, right? We just sort of talked about some of the history, some of the axioms behind these axiomatic systems. So the problems were hard to assign. They're a little bit different. And I'll just throw you a bone here. For example, the first one asks you to basically take Euclid's axioms, Euclid's postulates, and try to define some sort of notion of distance. And if you look at the SMSG axioms that we used, a notion of distance is postulated, it's axiomatized, right? We had the ruler postulate that tells us how to measure distances between points. And Euclid, of course, doesn't do that. He doesn't axiomatize any notion of distance, and that's a problem because you have to. So the answer to that question really is try and do something, but whatever you come up with, it's not going to be right. It's not going to be any better than anything I could do because there is no good way to define distance based on Euclid stuff. So try something, just try and come up with a notion of distance, but there's really no good way to do it. It sort of needs to be axiomatized. What else? There's a question about the alternate interior angle theorem, the converse of it. Think about the converse. Think about the converse. Maybe try and reword it a little bit in your mind, and you'll see pretty quickly that it's equivalent, I believe, to Euclid's fifth postulate. So it's not hard to see that. And that'll help, of course. I'm essentially telling you what the correct answer is to one of the questions. So, but anyway, let's get going here. We started on 3.2 last time. I don't want to do a whole lot this week. I just want to finish 3.2. And we went through the SMSG axioms, which was a lot of writing, a lot of stuff there, but it had to be done. So we've got that out of the way. And I've talked about the notation we'll be using while we were going through the axioms, but let's make it precise. So let's just be clear on all the notation we'll be using in this class. So AB with a bar above it, as we mentioned last time, this is the line segment. This is the line segment from A to B. Meanwhile, AB with no bar above it is the length of that line. So that's the notation I'll be using to distinguish between these things. Again, contextually, if you just use AB everywhere with no line, it's usually pretty clear from the context which one you're talking about if you get a bit lazy. And just again, a note, so this is nicer notation than we used in Geometry 1. Instead of talking about or having to distinguish between I'm going to extend my line, here we just have nice clean notation for it. AB with arrows above it is, of course, the infinite line. Is the infinite line on A and B. And I could even use a notation like this. AB is infinite in one direction, so it's just a ray. Like that, and so on. I think the notation is pretty good. Good notation is worth its weight in gold, really, and this notation is, of course, very suggestive as to what's happening. So there we go. And also with angles, again, so ABC is the angle. Is the angle ABC. And in Geometry 1, we use this to represent both the angle and the measure, and contextually it doesn't really lead to any confusion, but our textbook is going to be very precise here. When they want to talk about the measure of the angle, they'll throw a little m in front. So is the measure of the angle ABC. All of these next definitions, everything will be familiar to you if you took Geometry 1, but congruence of line segments, two line segments are congruent if they're the same length, if they have the same measure. Two angles are congruent if they have the same measure. So we'll be precise here. Two line segments or two angles are congruent if they have the same measure. And again, congruence is this idea of they don't differ under rigid motions. They might be in different places in the plane, but you can just pick one up and put it down on top of the other one, and it'll look exactly the same. So congruent line segments have to have the same length. And then once we have that, we of course have congruent polygons. So two polygons are congruent if, same thing, if they differ only by a rigid motion. Only by a rigid motion. And we could be very formal here. A rigid motion is sort of informal notation or informal language for what's called an isometry. This is a bijection of the plane that preserves distances. But I won't get this formal with it. I don't think we'll talk about isometries in this class. But a rigid motion is literally just pick up your shape, spin it around, whatever, flip it over, put it down on top of the other one. It should sort of overlap it perfectly. So that is if they have the same size and shape. Same size and shape. And a few basic theorems that we won't prove. The first one is that congruence is always an equivalence relation. So congruence, and here I mean congruence of line segments or angles or polygons is an equivalence relation. And you guys remember what equivalence relations are, right? I'm sure 201 must talk about equivalence relations a lot, and I know, and you've all taken 317. In 317 you talk about these things. Equivalence relations, you have reflexivity. A is related to A. If A is related to B, then B is related to A. There's a similarity or symmetry of the relation. And if A is related to B and B is related to C, then A is related to C. All right, we've got transitivity. So that's an equivalence relation in general. Here I'm saying Every angle is congruent to itself if I'm talking about angles, or every polygon is congruent to itself if I'm talking about congruence of polygons. If polygon A is congruent to polygon B, then B is congruent to polygon A, right? And if A and B are congruent and B and C are congruent, then A and C must be congruent. So congruence it works as nicely as you could possibly imagine. Two more very basic theorems. Every line segment has exactly one midpoint. Again, we won't prove these things. Can you see how you would immediately prove this? I mean, it's such an obvious statement that it's almost like, what exactly are we proving? But it sort of, it bears mention that it does follow immediately from our axioms, right? If I have a line segment, how do I prove that there's exactly one midpoint? Well, we have this notion of distance that we've axiomatized. In fact, we've said that line segments, we can put them in bijection with the real numbers. So just put your line segment in bijection with 0 to 1, and then the point corresponding to 1/2 is your midpoint, obviously, right? So nothing too fancy there. And every angle has exactly one bisector. So every angle can be cut in half exactly as well. Let's see. Theorem, this is from Geometry 1, vertical angles are congruent. Again, if you didn't take Geometry 1 or you haven't thought about geometry in a long time, a vertical angle is just take two transversals or two intersecting lines. The two opposite angles are vertical. So those two angles and those two angles. Again, these are sort of obvious statements. The proof from Geometry 1 that we use here will work exactly. They're obvious statements, but I want to remind you that we're not working in Euclidean geometry here. We don't have a parallel postulate to work with. So I'm restating these, and you should keep in mind that they're true in neutral geometry, meaning they're true in both hyperbolic and Euclidean geometry. So the proof of the fact that vertical angles are congruent doesn't rely on any sort of parallel postulate stuff. And another very simple one, supplements and complements of the same or congruent angles are congruent. So not a surprising result there either. Right, literally all it says is if I have an angle and I take the supplementary angle and I have the same angle over here and I take the supplementary angle of that one, they're the same angle. So nothing surprising, but here let's get into something new. This is usually called Pasch, I'm not sure I'm pronouncing this right actually, but Pasch's axiom. I think it's Pash. So it says the following. It says, if a line L intersects triangle PQR at a point S, such that, and I like this notation a lot, this textbook uses this notation all over the place, such that P, then S, then Q. It's very suggestive notation, but if you can't figure it out, I'll show you exactly what that means in a second. Then L intersects either PR or PQ. So what's this saying? I have a triangle PQR. Here's my triangle PQR. And I have a line that intersects the triangle at a point S. And what this notation means, the way you should read this in the textbook, we use this all over the place. I'll use it as well because it says quite a lot without having to write all the words that are obvious. It says I'm intersecting this triangle at a point S such that S lies on the line P and Q and between P and Q. All right, so there's a lot of words there, and words that actually in Geometry 1 we used to write out stuff like that all the time. This is nice notation for just saying S is a point on PQ and between P and Q. So here's what I have. I have a line L that comes through and it intersects. So it's sort of a very obvious feeling statement. It says, okay, if I have a line that comes in, then my line must eventually go out again, right? It has to leave the triangle. And in particular, it can't do something weird like this. It can't sort of loop back and cut through PQ to get out. It has to go through one of these two opposite sides. So something like that. This guy, Pash, I believe he came up with this in the 16 or 1700s, I think 1700s. He realized it was independent of Euclid's axioms, meaning it's something that you did have to axiomatize and Euclid didn't, so again, his axiomatic set is not complete. And I believe Hilbert, in Hilbert's axiomatic set for Euclidean geometry, he goes with this statement directly. SMSG doesn't. They use an equivalent statement, so we'll use the equivalent statement to prove this. They use the plane separation axiom that says that lines cut the planes into sort of two different halves. So it turns out this statement is equivalent to the plane separation axiom, and we'll write a proof. So since L intersects PQ at S with S on PQ and between S, we know that well, here's the plane separation axiom. If L is cutting through the line PQ at a point between P and Q, then P and Q are on different sides of this line. Right, so there's the plane separation axiom in action. Very obvious, but we know that P and Q are on different sides of L. And I'll make it very precise. This is the plane separation axiom. So we don't have to do a proof by contradiction here. I'm tempted to avoid it because people find them sort of aesthetically unpleasing if you don't have to do one. But we'll proceed by contradiction anyway. So let's say, suppose the conclusion's not true. Suppose L doesn't intersect PR or PQ. So suppose L does not intersect either PR or PQ. Well, if it doesn't intersect PR, as it doesn't in this picture, then plane separation axiom tells me that P and R must lie on the same side of L, right? So then P and R lie on the same side of L. I didn't mean to say PQ here, right? My assumption is that it cuts through PQ. I meant to say assume it doesn't intersect PR or QR. Sorry. Which means I didn't state Pasch's axiom correctly either, did I? So fix that as well. I said in the statement of Pasch's axiom, I said it intersects PR or PQ. Obviously it intersects PQ. So change that to PR or QR. Sorry about that. But anyway, then P and R lie on the same side of L. But if it doesn't intersect QR either, then Q and R lie on the same side of L. And also Q and R lie on the same side of L. What does that mean though? That means P and Q. Since they are both on the same side as R, P and Q must be on the same side as each other. And therefore, hence, let's say therefore. Therefore, P and Q lie on the same side of L. Which is a contradiction, right? Immediately we've contradicted the fact that, well, hold on, L cuts through P and Q. Contradicting that L intersects PQ. And again, I'm sort of the type of guy that would just end my proof here. Anyone who reads this would understand, yes, I have my contradiction. Therefore, my assumption, my contradictory assumption can't be true, and therefore the statement follows. But if you want, you can always just throw in an extra sentence. So hence, L must intersect one of PR or QR. Alright, so the reason this feels, the reason it feels so much like the plane separation axiom, and we're actually using it all over the place, is because it turns out it's an equivalent statement. So the plane separation axiom implies this theorem, as we've basically shown, because we use it all over the place. But the opposite's also true. And next up, we've got another rather famous, well-known theorem that the textbook doesn't prove, but I think we will. And it feels a whole lot like Patch's axiom. It's the Crossbar Theorem. So Crossbar Theorem says the following. It says, if X is a point in the interior of a triangle that we'll call UVW, then UX, which I'll extend, so not just a line segment UX, we'll extend this in the direction of X, intersects side WV at a point Y such that Y is between them. W, then Y, then V. Alright, so again, let's parse this. Here I've got a triangle UVW. I've got a point X on the interior, so here's my point X. And I'm saying, okay, let's take this line segment, let's take the line segment UX. And then let's extend it. So just keep going. Then the crossbar theorem again states this from this picture, a very obvious statement. The crossbar theorem says that if I extend this, it must cut through this opposite side of the triangle, VW, or I'll call it WV, at some point Y between them. Again, I want to point out that these pictures I'm drawing, these are Euclidean pictures, right? The situation might not look like this in hyperbolic geometry. In fact, straight lines in hyperbolic geometry are sort of curvilinear when I draw them in Euclidean sense. But this is totally valid. I'm drawing this picture because Euclidean geometry is a model of neutral geometry. It's a model where the parallel postulate holds, so this is a model of what's going on, and it's sort of suggestive of why it's true. So let's try and write a proof. So the proof is fairly clever. What I want to do here is I want to use Patch's axiom. And the way we're going to do this is we're just going to extend this triangle a bit. So choose a point T so that W, then U, then T. So again, in geometry 1, the way I would have phrased this is I would have said, take the line WU and extend it. Extend it in the direction of U to a point T or something like that. Here I very much like this notation. It just says choose a point T on the line WU so that T is collinear. So we'll extend this out to here. There's T. This gives me a larger triangle. This gives me the triangle TVW. So we're going to apply Pash's axiom to this bigger triangle TVW. Alright, Pash's axiom now applies here. I have a triangle with a line cutting through. So apply Pash's axiom to this triangle to conclude that UX intersects either VW or TV. All right, so I have this line. I have this line here. It's cutting through this triangle. So Pash's axiom says, okay, if my line came through TW, then it must leave either TV or VW, right? Which one is it? Well, I want to prove that it cuts through VW. So once again, plane separation axiom comes into play. Now, since T and W are on opposite sides of UV, it follows that T and X are on opposite sides of UV. And I suppose that's really enough. I suppose from here we can just conclude almost immediately that, okay, if T and X are on opposite sides of UV, then so are all points of this line. So are all points of the line UX. And therefore, this line UX has to cut through VW. Right, so let's see if I can, how quickly we can wrap this up. I think I'll say a few more words as we write this, but so yeah, let's phrase this slightly better. So hence, all points, in fact, all points of the line, all points of TV are on the opposite side of UV, as all points of UX. And therefore UX does not intersect TV. Therefore UX does not intersect TV. And so, by Pasch's axiom, must intersect WB. Sorry, this is somewhat easier to talk about than to write, so let's just, now that it's all written down, let's just step back and again sort of recap this. So we had this original picture, we had ux, and we wanted to show that when we extend this line, it must cut through the side BW. Right, that's what we wanted to show. The idea is pretty clever. The idea is, well, let's embed this in a larger triangle. So let's extend this to a larger triangle. And in this larger triangle, we just have we have Pasch's axiom happening here, right? In this larger triangle, we have Pasch's axiom. We've got this line that comes through and cuts through this side TW, and I want to show that it must leave through this opposite side. And, okay, so Pasch's axiom tells us it must cut through one of these two sides, but by using sort of this plane separation stuff, since I know that T and W are on opposite sides of this line, and X is on the opposite side, then there's no way it can sort of loop around and cut through here. It must proceed like that. Right, because this entire line is on the opposite side of U and V as T is. So there's the sort of famed crossbar theorem, and we will use it. We'll invoke this theorem quite often in proofs. Again, it's obvious in a Euclidean sense, but the point here is to prove that we don't need the parallel postulate. So it's true even without it. Right, it's just we're so used to drawing in Euclidean geometry that you're used to there's a straight line. But the truth is in neutral geometry, straight lines don't look like you want them to. So there is no real reason why a line couldn't do something like that. Right? What do we have? 8 minutes or so? We can do this real quick. This one will be very familiar to you. It's the famous Isosceles Triangle theorem. What does it say? It says if your triangle is isosceles, then your base angles are congruent. If two sides of the triangle are congruent, then the angles opposite these sides are congruent. Alright, so the famed isosceles triangle theorem. I believe in geometry 1 we actually proved this. The exact same proof will work here, but the point is that this proof does not depend on any sort of parallel postulate. So it says if these two sides are congruent, so I'm an isosceles triangle, then so are these two angles. The base angles of an isosceles triangle must be congruent as well. But we'll sketch a quick proof because it's not hard. So suppose for triangle PQR, suppose we have that PR is congruent to QR. Here the notation matters. If you're going to use this bar notation for actual lines, then it's congruence. If I'm talking about the fact that their lengths are equal, then if I'm using an equal sign, I would drop the bar, right? So depends on your notation. Now we invoke the crossbar theorem. By the crossbar theorem, the bisector of angle PRQ must intersect side PQ at a point T. With T between P and Q. So here I'm using the crossbar theorem. I'm saying let's construct the bisector of this angle. So we'll drop the bisector down. And this is going to cut through PQ at a point T. How do I know it cuts through a T? Well, this is, again, it's obvious in Euclidean sense, but that's not enough. It formally is the crossbar theorem that tells me that this bisector must cut through this opposite side. What do I know now? Well, I know, again, I'm trying to prove this. Because it's a bisector, those two angles are the same. Those two sides are the same. Those two sides are the same. So SAS is a postulate in SMSG, right? So now we can invoke SAS. We can say by SAS, those two triangles we've drawn are congruent. So now, by SAS, because PR is congruent with QR, RT is congruent with RT, and angle PRT is congruent with angle QRT. I don't like that I wrote by SAS so early. Let's just say now, because of this, then we'll invoke SAS. Then, by SAS, we have that those two triangles are congruent. Triangle PRT is congruent to triangle QRT. What does that mean? That means so are these other angles. These other angles are congruent, and just by identifying, corresponding angles, the result follows. So finally, by identifying corresponding angles, we have that angle, how do you want to call these? RPT. RPT is congruent with angle RQT. Done. So once again, the Isosceles Triangle theorem, I want you to keep this stuff in mind, is not just what you know from Euclidean geometry. That's not the goal here. The goal here is to establish what you know from Euclidean geometry is still going to be true in this class, in hyperbolic geometry. And the answer is isosceles triangle is still true, because we didn't have to use a parallel postulate anywhere to prove it. We'll stop here. We'll finish this section next time. And yeah, I'll see you Friday.